morning. Today I'll talk about a very exciting galactic transient and about its latest outburst. And I have titled my talk as Shock-Driven Synchrotron Emission from the 2021 outburst of RS Ophiuchi. This was a naked eye event. So, with a quick introduction, novae are luminous eruptions in binary systems in which a white dwarf accretes matter from its companion star. As the mass gets accreted, the temperature and density increases, pressure increases, and it triggers a runaway nuclear reactions at the base. And that is basically shown as this luminous flash, which is identified as novae. Now, novae, depending on the characteristics of the companion star, the novae are classified as different. Like in classical novae, the companion star is a normal main sequence star, whereas in a symbiotic novae, it will be a giant star. Now, ideally, every novae is expected to go on outbursts repeatedly, but novae where there are more than one outburst recorded, like in the human record time, are called recurrent novae. So why novae are interesting system? Because they are rich and complex and needs to be studied by its own merit. On top of that, they have a lot of implication on various other astrophysical phenomena like shock physics, radiative processes. Recently, there are TV emission detected from novae, so they serve as a very promising candidate for galactic cosmic rays, as well as particularly of my interest, they are thought to be as progenitors of thermonuclear supernovae. So let's dive directly into the radio emission from novae. They are multi-wavelength events. They are primarily identified in the optical bands. However, they show bright emission over a wide range of frequencies from radio to gamma rays. Like focusing on the radio emission from novae, there can be thermal as well as non-thermal radio emission. The thermal emission comes from the hot ionized nova ejecta, whereas non-thermal emission comes from shocks. So how does this shock happen? Like as the outburst happens, this accreted envelope is thrown to the circumbinary medium, the CBM, and that creates the shock, external shock, and particles can be accelerated to really high velocities and it emits synchrotron radiation. Now, this shocks or the non-thermal emission are characterized by basically two factors. One is very high brightness temperature and negative spectral indices, if I define the spectral index like this. So from the basic nature of its spectral behavior, thermal component of radio emission will be dominated at high frequency side and non-thermal component will be dominant in the low frequency regime. Now coming to the motivation of this project, what we were interested in is to look at the shock-driven non-thermal emission, radio emission from the 2021 outburst of this novae. So the immediate aim is to understand the property of circumbinary medium and shock. So a brief description about this event. It's a recurrent galactic symbiotic novae. There are not many well-studied system of recurrent novae. For example, in radio, there are only a handful of objects, like 10, where we have studied in detail. We means the community. So RS Ophiuchi has an orbital period of 453 days with a white dwarf mass very close to Chandrasekhar limit, and it has went through outbursts like 6 times with a like quiescent period of 10 to 15 years, and the latest outburst happened in August 2021, and it was a bright event and were followed using various telescopes over radio to gamma rays for a long time, like more than a year or so. So what we did is to look at this event with the uGMRT at sub-gigahertz frequencies. We started our follow-up observations from roughly 23 days post the outburst, and we have been following this object Like even now our follow-up observations are happening, but what I will be presenting is till the roughly 287 days post the outburst. So here are the radio light curves at 4 different frequencies from 0.15 to 1.4 gigahertz. And this 0.15 light curves are the only existing lowest frequency light curve of any recurrent novae till date. So these are we were looking into the characteristics of this radio emission. First, we wanted to know what is the origin of this emission. Is it non-thermal or thermal? And these are the spectral indices. They are predominantly negative, which implies that it's of synchrotron in origin. And the corresponding brightness temperatures are of the order of 10 power 5 to 7. And the evolution of radio light curves are also interesting. As you can see, all the green, red, and blue points are tracing from a peak to decline, whereas the lower frequency, you see a rise and a decline. So this is a typical behavior seen in radio supernovae also, because as the shock propagates to the surrounding medium, there will be also absorption processes on top of the emission. Now the absorption process or the absorbing the optical depth is wavelength dependent. So higher frequencies will be showing up first, and the lower frequency will show up later, because there is more foreground absorption towards the low frequency side. So it's very similar to the evolution of radio light curves. So these are the typical radio light curves of supernovae. So we went ahead and decided to model this light curve evolution adopting the synchrotron emission model originally developed for radio supernovae. So this will be the typical analytical form with a absorption term as well as temporal and spectral evolution, which we need to basically model. And the absorbing components we take two. One is a uniform ionized medium and one is a clumpy medium in the line of sight. So these are the best fit model for different frequencies. As you can see, they are fairly well represented by the shock-driven synchrotron emission model. And these are a few best fit parameters which are of interest. One is the optically thin spectral index, which is minus 0.5, and a temporal decay index of -1. This kind of a decay index is typically expected for a density fall of 1 over r square, which will be basically created by a stellar wind of uniform nature. And this is another interesting parameter, which is the shock deceleration index, how fast the ejected shock is slowing down as it hits the surrounding medium. And this is a very relatively small in number if we consider the typical numbers that we see in radio supernovae, which means that the shock is significantly decelerated in compared to typical supernova. Other important aspect which we found is the contribution towards absorption by homogeneous and inhomogeneous medium. The absorbing component is predominantly clumpy. And we also derived the Maslow's rate of the red giant stellar wind, assuming a stellar wind velocity, which is to be of the order of 10 power minus 6. So, as I mentioned, there were 6 previous outbursts for RS Ophiuchi. Out of these 6, 1985, 2006, and 2021 were well observed and monitored with multi-frequency facilities. So, we wanted to go back and look at the radio light curves from the previous outbursts to study the evolution of the system in terms of mass accretion and shock physics. So in the figure, you see the comparison of similar low frequency light curves which Kantaria obtained in 2006. These are in black and blue is the 2006 and the red one in 2021. So there is a significant flux increase in 2021. It may not look that high in the plot, but this y-axis is in log scale. So the difference in flux density at different frequencies is of the order of 20 millijansky, which is a lot. So we interpret the higher synchrotron emissivity in the 2021 outburst to be due to a more number of particles in the synchrotron emitting plasma. Another important aspect of 2021 and 2006 comparison is here. So as I mentioned, the way lower frequency turns on and the time at which low frequencies are turning on depends on how much is the foreground absorption. If the low frequency turns on earlier, which means that there is less absorption for those frequencies in the line of sight. So if we see, there is 0.15 gigahertz detection in 2021, whereas that frequency emission was not seen in the 2006 for similar sensitivities up to a day 150 or so. And similarly, if we compare 2006 and 1985, like 0.33 gigahertz was detected in 2006, but for similar sensitivity, that frequency emission was not seen in the 1985 outburst. So at least in last 3 outbursts from 1985 to 2021, there is a systematic trend of lower frequency emission turning on at earlier times. So this has to be due to lower absorbing medium in the foreground. But why exactly it is happening? What is the spatial distribution of this material in the line of sight is something which we need to yet understand. But this is observational fact, and it's fairly clear that there is a systematic trend, at least in the last 3 outbursts. So this is the summary. We look at a long-term evolution of low frequency emission from RS Ophiuchi, and we see that it is a shock-driven synchrotron emission absorbed by a clumpy plus uniform medium. And we see that lower frequency emissions are turning on at earlier times, and this has to be due to lower foreground absorption in the successive outbursts. This event is one of the unique event of last maybe 20-25 years, and the event is still of the order of few millijansky, and GMRT can go up to 10 to 20 microjanskys. So we have data yet to be analyzed up to day 500 or so, and we are planning to submit the follow-up proposals for cycle 44. So with all of this, it will be like one of the best sampled recurrent novae till date at sub-gigahertz frequencies. And we look forward to many more of these events in the area of SK. Thank you.
Thank you.
Yes.
So one thing is that what kind of absorption you are considering is synchrotron self-absorption?
No, so we consider free absorption due to the external ionized medium. Yeah, so one can, so I in fact tried with synchrotron self-absorption model as well, but that gives a worse fit compared to the free absorption model. Okay. So the best fit model takes care of the free absorption due to the ionized subcombinatory medium, which is ahead of the shock.
Okay, so you fitted it on the light curve?
Yes.
And in spectrum?
So it's a 2D fit. Like we keep both frequency and time as the variable and keep all the free parameters. So it's like a 2D fit. It's f of mu t is what we are fitting.
Sorry.
Is there any possibility having any polarization studies of these sources to nail it down the synchrotron?
So for the magnetic fields you are saying, yes. I am not aware of such a study yet, but that will be interesting.
We are saying synchrotron, then we should see the polarization linearly polarized, and then there is the observational evidence of that.
Yes, yes.
You said the ED emissions.
Yes.
So people also find cosmic wave used element production.
So not element production. So this is the first novae where TV emission has been detected. So there are models like there are detection from HESS as well as MAGIC. So what they model the multi-frequency. There are also hard X-ray detection, GV Fermi detection is there. So they take into account this multi-frequency light curve from X-ray to TV and say that the observed flux in these different wave bands are well represented by a hadronic particle acceleration model where particles can be like protons can get accelerated to cosmic ray energies. So, yeah.
Okay. Yeah, still?
Whether it is theory is not doing the there,
Yes, yes.
it is not only hadronic.
Yes, most of the literature are in support of the hadronic, like a single shock, single zone hadronic model.
So, one quick question.
So is it possible to compute the Mach number for shock strength?
Yeah, I need to think about it.
Because you already plotted this spectral index.
Yes. So Mach number we can get just from the spectral index. So
Yes, but your spectral index is minus 0.5.
yes.
It's quite good.
Okay.
If it is a pure diffusive shock acceleration, then you can estimate easily.
Okay.
Otherwise, it will be complicated.
Okay. Okay. Yeah. So a rough estimate one can get.
Okay, thanks, Nayana. Next one.
Long live India and France friendship.